Thanks, John. Thanks for having me back. It's always a pleasure to be here. I don't know how I can get rid of this little slide thing, but that works. Yeah, beautiful. Um, so here to talk a bit about one of my favorite topics, which is negative triangularity in tokamaks. And we'll learn what that means and why it's pretty cool over the course of the next discussion. Um, this is turning into like a fairly large international effort. So we kind of started ramping up about 5 or 6 years ago, and then in the past few years, we've had a lot of really great data coming out of the machine San Diego. And I'll show you a lot of that data today. This will be a mostly like data and interpretive based presentation, but it also has some theory in there. And then depending how far we get, we can talk about other things and extrapolations and stuff like that. So just to touch base with where we were in the last time I was here, right, we're trying to make fusion energy. There's lots of different strategies to do this, and you can characterize them in lots of different ways. One of the most popular is looking at sort of this approach towards ignition or steady state operation. So temperature here on the x-axis, NT on the y-axis, the product of these two is NT tau, which is our triple product, which we talked about last time. And there's three main approaches. There's laser-based approach, which is what people like CSU and NIF in California are really focusing on in Rochester. There's the magnet type approach, which is mainly led by tokamaks. You can see D3D here, which is a tokamak we'll be talking a lot about today. And then there's alternative concepts. So just to kind of paint the scene, we're mostly talking about magnetic confinement fusion today, entirely talking about magnetic confinement fusion, entirely talking about tokamaks. But all of these strategies have had their own real thrust towards creating these fusion relevant conditions over the past several decades. And the main lever and the main like moving the needle of this thrust has been the goal to achieve really high performance, right? Because if you look at plots like this, what's plotted on the y-axis really is your plasma performance, and we just want to get that up to a level where it's sufficient for fusion to occur. And so this high performance lever has been really driving a bunch of research in all the different subfields, tokamaks notwithstanding. So the tokamak path is this red path here. Um, there are two really common metrics that you might see in the literature. One is this normalized beta n. Normalized beta is a common plasma parameter for tokamaks. Our goal is something like 1.5 to 3%. So these are always given in percents in tokamaks. It's fairly low on the grand scheme of things, but it's really good for fusion. Turns out to be very, very difficult to do harden that. And then we have a normalized confinement factor, H98, which also is describing performance. And this is really just a multi-machine scaling. It's entirely empirical. You can write it down. And if you have H98 of 1, you have like an average H-mode plasma performance, which we'll talk about that in a sec as well. So in the tokamak line of research, we've been really pushing towards getting towards high performance, but this kind of bypasses a couple other issues. So I would say that these are not really reactor compatible. One, because they're not a high performance, but two, because they have issues with exhaust and issues with reproducibility. So this high performance that we achieve in tokamaks these days is generally achieved via H mode, which is a very common term in tokamaks. It refers to a very small region of the plasma out here. So this is my normalized radius from 0% way over here to 100%. That's the closed flux surface at the outside of the plasma. And just in this tiny little narrow region by the edge, we can raise up a very steep gradient of the plasma pressure. And this is a pedestal that we're basically putting the rest of our plasma on. So when you have this pedestal, we're in H mode, and we can talk about why that happens. Really, the leading understanding is it's the sort of predator-prey effect that occurs with your E cross B rotation. And so if you have E cross B shear in your edge, basically you're shearing away your plasma, any sort of turbulent eddies that would have otherwise been transporting stuff out of your plasma start to get broken up, and you introduce like a transport barrier, which is preventing your plasma from leaving and raising up a pedestal. This is really great. You get improved beta, you get improved H, usually about 2 times greater than L mode, though in this plot it's quite significantly higher than 2 times. It's just an illustration. But this says nothing about exhaust, right? We have to have this star in a bottle be compatible with machine walls somehow. And it says nothing about reproducibility. And these high performance H modes that really take the cream of the crop for producing pressure records and performance records don't really talk about either or deal with either in a sufficient way. So for example, this is a run day from the D3D machine in San Diego, where most of the data we'll see today is coming from. Typically, when we're looking at tokamak plasmas, we have something called like a trophy shot. So someone will run an experiment for a week, try a bunch of new stuff. Their best shot will be their trophy shot. That's the one that they publish, and then they go around and describe and look at the physics in great detail. In this case, it was this black line, this beta n of almost 4, which is way higher than 1.5 to 3 that I was saying, right? Has relatively low MHD activity. But in the colored plots here, I've also overplotted every other shot around that, right? And these were not like complete scans. Like a lot of these shots were trying to do the exact same thing. But either you have something going interesting in your plasma, you have some MHD event that kills your H mode and your beta drops significantly, or you have some other fault, or even in non-H mode scenarios, you might be in like a very tricky performance regime where you need to be just right and navigate these like stability windows, and it's very hard to do. Obviously, reproducibility is very bad for your capacity factor in actually producing electricity. And so this is like kind of an unstated issue with a lot of tokamak plasmas. The one that gets a little bit more traction in the research sphere is the exhaust problem, which is controlling the heat and particle exhaust. If you imagine we have, a star in a bottle and it's propped up at this giant steep temperature gradient, what ends up happening is that all this power that's leaving the plasma core has to flow through something and eventually end up somewhere. And what ends up happening in a diverted configuration for a tokamak is your power leaves the core, it flows out to this red line, which is a separatrix, and then it will basically get condensed right around the separatrix because it's following the field lines faster than it's traveling across them into a very narrow region, which can be something like 1 to 10 millimeters. And we call this a scrape-off layer width. Depositing all your energy on the scrape-off layer width, if you scale it towards a reactor, gets you way above material limits that we can possibly tolerate. So typically you'd have only be able to tolerate a few megawatts per meter squared before you melt. In just steady state operation, if you don't do anything special, you're looking at like 30 megawatts per meter squared, 50 megawatts per meter squared in tiny little places on the metal. And so people have done a bunch of simulations of this. This is an example of like actual heat flow traveling through this configuration. You can see it's really concentrated in very small components. There's fancy ways to deal with this. The easiest way to deal with this is just to get rid of the power before it hits the scrape-off layer. So you can do that through radiation, but then radiation has its own problems. It dilutes your core, or it eventually dilutes your fuel, or it causes instabilities of its own. And then last time I was here, we also introduced the idea that transient events can even further complicate this picture. So if you have a steady state heat flux that you can tolerate, in H mode, we have this big steep gradient, and we used an analogy of a bucket, right? Here's your H mode stopping the plasma from leaving, but all buckets will eventually overflow. In tokamaks, the same sort of thing happens. Eventually, you hit the stability limit that is at the top of this gradient, and you have an ELM, which is a big instantaneous reconnection of plasma that connects your core to the edge region and produces big transient heat fluxes on the machine walls. In today's tokamaks, that's not really an issue because our tokamaks run at low IP and low power. But if you scale up IP from today, which is usually like 2 megaamps, towards where we want to operate a fusion power plant, which is like 15 megaamps, the energy that you're depositing with an ELM goes up. And it turns out that due to the rest of the configurations, the energy required to melt the edges of your tiles or the surface of your tiles goes down. And this is really, really bad. And you can do like a simulation, and it kind of looks like this when it's happening. This is not a simulation, an experiment trying to do this from Russia. Melting your tiles is really bad. They're typically made of tungsten. You put tungsten in your core, tungsten radiates like crazy, and your plasma loses all of its energy and dies. So not to mention you melt the machine, which is also to be avoided. So these must be avoided in a fusion power plant and are one of the key factors of HMUD.
So that there's a whole campaign, a lot of work at D3D to do help, and not just D3D, but other places to do ELM-free regimes, right?
Yeah.
Custom QH mode and other things.
Absolutely, yeah. So there's lots of different strategies to avoid ELMs. It's like an obvious issue, and so lots of people are looking at it in different ways. Negative triangularity which is what we'll talk about today, is one of those strategies. And then there are others, like Scott mentioned, like wide vessel QH mode, I mode,
Adding coil, I heard they call it.
RMP coils. Yeah. If we want, I have some slides at the end that we can talk about, like comparing all these different regimes. Yeah, there's lots of strategies. Some of them are really, really fragile, and this one I think is the best. So hopefully we can kind of see that. Yeah, so what is negative triangularity, besides the best ELM-free strategy? It's really just a simple shape change. So this on the right is how most, by most I mean like 99.9% of tokamak plasmas are run. With, I mean, you can, a bigger, basically it's an outward facing triangle. It has a bigger length here than it does on the outboard side. And this is the same shape as the machine itself, because all these machines are designed exclusively to run this shape. Negative triangularity just flips that. And so we go from big on the inside to big on the outside, imaginary torus kind of going around this way, where it's a cross section. And you can see it doesn't really fit in the vacuum vessels. We're actually really lucky that we can do it well on D3D, because you have to get lucky with how your magnetic coils were put in, because they were designed to do this. But D3D is fairly flexible in the shaping capabilities, so we're able to explore this configuration. And that's been really useful.
If you did design the machine for this, would you change it to fit?
Yeah, so we could change it. And we've done a couple studies like that. No one's built one yet. Maybe soon. Yeah, please. Yeah. Great question. So, I mean, the short answer is it doesn't. In theory, you could kind of do any shape you wanted to. In the 70s and 80s, people were looking at what is the best shape for a tokamak, and they have kind of revisited that question over and over again since then. There are a couple sort of shaping moments that really improve performance for various reasons. Triangularity is one of them. Elongation is one of them. That's how stretched out you are. And then squareness is another one. And basically, like the more triangularity you have, and the better your MHD stability, and so the higher your beta limits, and the more performance you think you can get out of it. The more elongation you have, the larger your volume, so the more like fusion power you think you can get out of your scenario. So these shaping moments all have their own effects. And this triangularity moment was actually abandoned in the 1780s precisely because it was predicted to have much lower beta limits, right? So we thought if we go to really high triangularity, and this is really easy to show just through ideal MHD, you'd get, there's really high positive triangularity like this red shape, you'd get very strong beta, and that's good. So we all went towards strong beta. And that's still a true picture. And so kind of the message of negative triangularity is, yes, we get slightly lower stability, but that actually turns out to be a good thing now, because we've improved the rest of our plasma enough that this lower limit on the total achievable performance is not detrimental towards actually accessing fusion relevant conditions. Rather, it's just it saves you in some other places. So it's like a trade-off, basically. So it was originally abandoned for that reason. But in the early 2000s, there's a tokamak in Switzerland called TCD, which is really, really flexible in shaping. It's literally just a rectangular box, and they can make any shape that they want. And they started to notice, playing around, that you can get improved confinement in L mode only if you go to this negative triangularity shape. And so that's shown here. This x-axis is 1 over collisionality. That's just like a scan your plasma space density over temperature. The y-axis here is your heat transport, Chi. And so the positive triangularity shots have higher heat transport across all of the different collisionality compared to the negative triangularity. And thus, negative triangularity just in L mode, not looking at H mode, is performing better than positive triangularity. Yeah.
Can you remind us briefly what H and L mode is?
Yeah. So H mode is the main confinement regime that you're going to see. It's really characterized by the super strong gradient of pressure in the edge region. And so if you have like an L mode profile like this, and then you add in a pedestal, your H mode profile is up here, and it's just greater throughout the entire region. And we'll talk a little bit more about like the differences in stability in a bit. Yeah. But this experiment was quite exciting for the field because it showed like a potential way to improve L mode, and maybe that's worth looking into. So in 2023 on D3D, we revamped the whole vessel. We installed a whole new set of armor. Basically, you can see these are ports that used to house diagnostics. We just covered them up with high heat flux tiles, which is kind of shown here in the cross-section view. And this allowed us to make a bunch of new shapes with high power that were previously inaccessible because they would have been shooting power onto your diagnostics. And there were a bunch of, this was like a 2-month long campaign compared to usually you have like half a day for an experiment. So very, very dedicated effort. 13 dedicated experiments covering lots of different things. And we really expanded the parameter regime quite a bit. So you can see kind of an old discharge, an old data set of where we were supposed to be in gray. And then the new negative triangularity discharges are all in green. And most of what I'll show today came from this campaign and analysis that followed.
Why are the points bleeding into positive triangularity? Is this something that you can't determine completely beforehand, but you have to measure?
It is something we can determine. These are actually some shots that I ran. We were looking at like where this negative triangularity effect kicks into gear. So typically D3D will run with triangularities of like 0.6 to 0.8. So going down to like 0.1 is already way lower. And so some of these, and this is all in this hybrid shape here. So you can see the X points in different places. In the hybrid shape, we're actually able to take the top triangularity and kind of move it back and forth. And so if you average the triangularity on the top and the triangularity on the bottom, you can go like across 0 from 0.1 to minus 0.1.
What are you actually changing to change the triangularity?
Coil currents in your coils. And this is controlled by a bunch of segments that we're measuring with probes. The D3D control system is really nice. Yeah, lots of flexibility.
You control the toroidal currents with RF or with external transformer drive. I just want you have some control over the toroidal.
We have a little bit of control via RF. That wasn't studied much in this campaign. Actually, since this concluded, there have been more like current drives. This was mostly like 90% external coils. There have been a couple more studies on D3D since then with like fancy ways to drive current with LHCD or with helicons. The theory for all those says that they'll be better at higher currents, which we can't access in D3D, and hotter plasmas because your resistivity goes down. So maybe that's more of a thing for future reactors than it is for today's experiment. So for the rest of the talk, that was kind of like an intro. I wanted to talk more about what is this actual boundary condition, what is preventing ELMs and NT, how does this change the performance, how does that all look? We can skip through this if you want and talk about some other physics topics or design of reactors with NT. I have a bunch of slides on those, but we'll just kind of plow ahead until it's time to move. So to talk about the ELM problem, we first have to understand what ELMs are. Hopefully this is an equation that all of us recognize from your first or second plasma physics course. I think Scott first showed me this equation back in the day. This is delta W. It has lots of different terms in it, right? These upper terms are all squared, so they're all positive and stabilizing. These are waves. And these lower terms are instabilities. We have two main ones, right? We have one, which has a pressure gradient in it. This is coming with the interchange and ballooning modes. We have one that's current driven, and this is your sausage and kink instabilities. In toroidal geometry, you still have delta W. You can resolve it slightly. It becomes a little bit more complicated. We term these then peeling, the current driven, and ballooning, the pressure driven modes. So you can calculate what all of these ideal or these MHD modes turn out to be. And in the toroidal geometry, you can put them on an axis like this, where we'll have our pressure gradient, which you'll see many times. This is alpha, normalized pressure gradient, and then pedestal current on the y-axis here. Ballooning modes are destabilized by the gradient pressure, as we know from delta W. They're stabilized by current. And peeling modes are the exact opposite. So you kind of get boxed in terms of where you can have your current, where you can have your pressure, without running into either a ballooning mode on this side or a peeling mode up on this side. And so we'll see examples of this. I'll show data in a second where you have an unstable region and a stable region. And the ELMs are basically what happens when you run into the stability. So if you imagine we have a pressure gradient here and a pedestal current, because there's always some current in the pedestal. We said we were shearing apart all our turbulent eddies, so we're growing up in this transport barrier. Our pressure gradient's increasing. Eventually, it can't increase any further. We hit the stability limit, right? Any trajectory that you're on, you're going to hit the stability limit. And when that happens, you trigger a reconnection event. You triggered a peeling ballooning mode. you lose a bunch of pressure gradient, you lose a bunch of current, this all gets distributed out to the scrape off layer, and you end up sort of in a cyclical cycle like this, where you're transiently dumping a ton of power out into the region. So this is, again, that same plot. We have current on the y-axis here, alpha, pressure gradient on the x-axis. This is real data from a D3D shot. We can have a stable region and an unstable region. We have some boundary, and the maximum pressure that we're able to achieve is like right on this boundary. So this theory agrees really, really well with the experimental data that we were able to see. And this is consistent across hundreds of shots. On the bottom here, I'm plotting D alpha light. D alpha is a diagnostic we have that just measures the D alpha light from recombination of hydrogen in the scrape off layer. So when our hot plasma enters this cold scrape off layer, produces a bunch of light, and we can measure that signal. In the stable region, you would have something like this, where it's just kind of sitting along. Maybe there's some transient bumps. When you have an ELM, you have this huge spike in D alpha light. It spikes up really quickly and sort of decays. This is the same thing if you're going to measure heat flux. It would spike up really quickly and then it would decay. So that's sort of what we mean by an ELM. There are these transient events that are really quickly depositing heat flux. Yeah.
This, like, the periodicity of these spikes is of the same process you just described on the previous, like, the slide with the ballooning modes.
Exactly, yeah. The periodicity is set
Very
here.
quick, like milliseconds.
Yeah. It's you're triggering a reconnection event, and it goes poof,
And then again.
and then again and again. Yeah, and this period is variable. Like depending on where you hit, this is hitting kind of the nose right on. Depending on where you hit the stability boundary, you can get different types of ELMs. Some, like basically some are more ballooning driven, some are more peeling driven. And this changes how much energy they're depositing, how quickly they're redepositing their energy. There's a lot of study of that as well.
But also, it takes time for the pressure gradients to occur.
Exactly, yeah.
That's what the delay is.
Mhm,
That's it.
Yeah, so there's lots of different types of ELMs. I think here I didn't label it, but this is like a strong type 1 ELM, which is the main one we're worried about. But you also see type 2, type 3, type 4, type 5, type 6A, etc. Yeah, please.
Is your purpose to increase that period or to get rid of that?
There's well, yeah. I mean, for an FPP, we want to get rid of them entirely. We have to get rid of them entirely. There are strategies to do this that basically say, okay, well, what if you, instead of getting rid of them, you just trigger them like all the time, so they're kind of constant. This is where like QC or EDA, which are other strategies, come in. They're very rapid, small ELMs, which maybe are okay. If you look at like the highest performing discharges on D3D or something, these all have giant ELMs, which are really far apart. And so you have like a really steep buildup of pressure and stored energy. You get to your record plasma pressures and you get a little trophy, but then you dump it all into the wall. So depending on what experiment you're doing, you might be aiming for different things. Yeah. So this is the this is a plot in time of a negative triangularity discharge that we ran, where the triangularity delta here is moving from negative to 0 and then back to negative. So this is one of those ones that we were talking about. It's like right on the border, right? And the important parts here are the power is constant. So I'm not changing anything fancy in the background. But my D alpha is definitely not, right? So when we're at negative triangularity, our D alpha is very, very smooth. It's ELM-free. And then as we go to more 0 triangularity, we get these giant spikes in the alpha light. Same spike Q outer strike point is our heat flux deposited on the walls. This goes up as well. And then as we come back down, eventually we re-enter this ELM-free regime without the big spikes, and our heat flux steadies out.
What is the power of the spiking stuff?
This one?
The second panel.
Oh, the
power.
Right. So the power injected, this is from neutral beams. And the way we run neutral beams on D3D is to modulate them for a couple different reasons. One, it's easier for the actual equipment to not be on full all the time, to run duty cycles basically. But then 2, it also allows us to fine tune how much power we're putting in. You can change your duty cycle to have a linear ramp. And then 3, it allows for diagnostic coverage as well. So these 2 spikes, actually, some of our diagnostics that measure ions need a neutral beam. It's charge exchange, and it needs to look at a neutral beam. So we put in like really quick blips of that neutral beam to hopefully not change the power too much, but to still get the diagnostic measurements that we want. Right. So this is all controlled. Yeah, so in our bucket analogy, this is basically, there's something going on here, which is poking holes in the bucket. It's preventing it from overflowing. And that's really what we want to look at today. This is that same sort of data, but this is just plotting instead of one discharge, over 1,000 discharges to show that this is a reproducible effect. This plot is probably the only one we'll talk about right now. We can talk about the others if you'd like. But there's colors here. ELM-free is blue, H-mode is red. Triangularity is on the x-axis. And power, FLH, so power over the power that we think we'll need to put in to get into H-mode, fraction LH of power, is on the y-axis. So typically you'd expect H-mode to be around 1 or up there. So if you see it near here, there's no H-mode at very low power. But no matter how much power you put in, if your triangularity is negative enough, you just can't get at H-mode. It's a super robust phenomenon. We're unable to, over 1,000 discharges, ever trigger an ELM if the triangularity is large enough, which is really, really reproducible and really, really robust. So that's one of the unique things about negative triangularity compared to these other ELM-free regimes. Those are much more fragile usually, and you'll never see them for a full pulse. Even within one discharge, you'll see only a period of that ELM-free. But for here, we can see it for 2 months in a row.
But that's because you don't have good confinement at the pedestal.
Well, it's not as good, but it's good enough. So the beta here and the pressure at the pedestal are both kind of measures of that, which is why these are included. And you can see that the top of these betas are this is around 3, right? That's about where we wanted to be for a reactor. And these pressure pedestals, it's not actually the pedestal, it's a little bit further in, maybe 0.8 instead of 0.9. But we're able to get to good pressures comparable or above where we were with H mode. Right, so even though it's not like as good as the records you've ever had on T3D, it's probably still good enough for a reactor environment.
So is the picture here that if you're in negative triangularity, you never build up gradients as much, so it never go unstable because of that.
That's the picture. Yeah. Yeah. And yeah, so that's kind of shown here, right? So this is again our same plot, current on the y-axis, alpha on the x-axis. Our stability line for peeling ballooning modes, this is a reconstruction of actual data here, is way out here. So if we were up here, we would have ELMs. This would be where our H modes would live. Instead, we have an ideal ballooning limit, just the ideal ballooning limit, without peeling balloonings, which is kind of this dashed line here. And that is where all of our experimental shots for negative triangularity end up. They end up on this ideal limit instead of the peeling ballooning limit. And so we'll talk about why this happens. Just to quickly give terms to things, in this graph, we have historically referred to 2 separate regions. One is the first stable region below the ideal ballooning limit, and one is the second stable region above the ideal ballooning limit. In H modes, this kind of all blends together because you can't see the ideal ballooning limit, and we'll see that in a sec. But negative triangularity plasmas basically have closed access to the second stable region. They can't get there, and so they're prevented from going all the way to that really damaging instability.
So with negative triangularity, do you have an L mode or is it a different?
This is a debate that we've had in the control room about what to call it. I think it's not an L mode. The original papers call it an L mode, but we'll see why I don't think it's an L mode later on too. I call it an NT edge because it's the edge of an NT.
And so do standard L modes with positive triangularity also not have ELMs?
They also don't have ELMs, yeah.
But they can't reach the parameters that you need.
Correct, yeah.
So, if it's a reactor, you have to have a high density and high temperature in the core, right? So, is that can you get a high density and high temperature?
Yeah, we can. So just skipping ahead a little bit just to engage the discussion, right? This is 3 different discharges at relatively matched conditions. So same plasma current, same magnetic field, same volume average density, same power. The L mode is at slightly lower beta N because it's lower confinement. But you can see a comparison here between L mode, negative triangularity, and positive triangularity, right? So the positive triangularity has this huge pedestal right at the edge. And then it's kind of flatter inside. Negative triangularity has a little pedestal. There's something happening here at the edge for sure. And then it's a little bit steeper throughout the core. So this enhanced steepness in the core is what that TCV experiment saw originally, right? It was a little bit better confinement in the core. And it turns out that this little bit better confinement in the core plus a little pedestal gets you to enough performance that you can compete with some of the H modes. If you compare that to the L mode is very flat in the core and very flat in the edge, right? So it's a significantly different confinement regime. So yeah, we're not as good as the best H modes. We can't be, because then we'd be triggering ELMs, right? They're good enough. And yeah, we can look at reactor design too
It
later.
wouldn't necessarily be triggered. It depends on the core confinement.
Depends on the core confinement.
Yeah.
Yeah.
At the expense of the edge.
Yes. Yeah. The core confinement is improved at the expense of the edge confinement.
Can you give a sense of
I mean,
how,
I'm not pro.
Yeah. No,
That's PT or anything.
Yeah,
I'm
yeah.
Just trying to.
no, those are real. Yeah, those are real facts. Yeah.
how much could you tailor the H mode? Like, could you sort of bring the H mode down a little bit closer to the anti-ELM-free?
Yeah. No, absolutely.
Would it have similar? Would it still have ELM problems?
So, yeah, there's like two ways to do that. There are ways to make like a worse H mode. These still have ELMs and they're worse. And so people don't really like them, right? Because they don't solve any problems and they're just worse. This would be like, for example, like putting in a bunch of radiation or decreasing your shaping, going back towards something more oval-like. As we've mentioned, right, there's other strategies to do ELM-free H modes. So like a wide pedestal QH mode, which is one of these strategies, basically has the same pedestal height, but instead it's over here somewhere. So it's a wider pedestal. That decreases your gradients, right? And if your alpha is not as strong, you're not going to be hitting that peeling ballooning boundary, so you won't be ELMing. But you can still have very similar core confinements. So these are really, really good performing discharges with an ELM-free edge. They have their own sets of issues, primarily being they're very difficult to trick the plasma into getting to that exact point. So you need like a very precise rotation. You need a very precise impurity content. We've demonstrated really good ones for half a second on D3D out of a 5-second D3D pulse. But you can't remake it on Aztecs in Germany because even though it's a very similar plasma, because they have a different impurity content or something. So they're more fragile. Then you also have cases like QCE, which is quite robust, which is basically just like reducing this pedestal height. RMP works similarly. Resonant magnetic perturbations puts in like an external force to drive some transport in the edge. You reduce your pedestal a little bit. These then have like a similar width, but slightly reduced height. The core remains about the same. Those are also good, but have their own dilemmas as well. Negative triangularity also has dilemmas. None of them are perfect, but it's definitely the most robust out of all of them. Yeah. It seems like we should definitely show some of the plots comparing everything at the end before we leave today. Right.
This is not a tokamak crowd. This is a
Yeah.
basic plasma.
Right.
ICS.
Which is why we started with the delta W. That's relatable, hopefully. Yeah, okay, so let's see. We can skip these slides.
But we greatly appreciate all the effective material.
Yeah, absolutely. Happy to chat through it. So I think this is one of the ones that I think helps me visualize what's happening in NT-Edge the most. This is just a model scan. So these are not real data. This is a model going from positive triangularity in blue to negative triangularity in red. And what we're plotting here, this is the same ideal ballooning stability that we've been talking about, but now on different axes. The x-axis is the radius, right, normal radius from 85% to 100%, right towards the edge, right in the pedestal region. Pressure gradient, alpha, is on the y-axis now. And there's two sets of lines. There's a dashed line, which is what I'm prescribing as my pressure gradient. This is the pressure gradient the edge. So if you look at the dashed line, it's flat and then it has a spike. This is a steep gradient region for the pedestal and it comes back down, right? So this is the same pedestal, just visualized differently. In the solid, we have instability curves. And so for the blue curves, the positive triangularity, you can see that there's an instability right here, which is well above where we have our gradient. There's a little bit of instability right here, but importantly, there's a blue instability limit right where the pedestal is. So in positive triangularity, you have a gap in your stability limit for ideal ballooning, which lets your pedestal grow up. In negative triangularity, this gap doesn't exist. The instability line goes all the way across. So this is actually an unstable plasma because my pressure gradient is over this instability line. If I was going to make this stable and realistic, we would have to reduce the gradient in negative triangularity to these red curves here. So now none of these lines cross the instability threshold. The blue one's able to maintain a really strong pedestal. As we go to negative triangularity, our pedestal has to be reduced. And you can actually trace this back in the ballooning equation to shear. It all just comes back down to magnetic shear in the edge. So we can define our local shear, something like this, as magnetic shear and pressure gradient with the cosine of the toroidal angle. A little bit irrelevant, but the stabilization for these ideal ballooning modes, this is the relevant part, goes like shear squared. So if I have very large shear or very low shear, I will be stabilizing infinite ballooning modes, getting rid of that instability boundary and letting my pressure gradient grow very high. If we compare something with negative triangularity to something with positive triangularity, in positive triangularity, we have very, very low shear on the outside, very, very high shear on the inside, and we have a crossing of zero kind of near the peaks. This crossing of zero is where shear goes to zero, so your stabilization term goes to zero. But we also have in tokamaks something called good curvature and bad curvature. Good curvature is on the inside, bad curvature is on the outside, and the curvature is also stabilizing or destabilizing for the ballooning modes. So because this shear crossing happens near the peak, it's in the good curvature region. And when your shear is suppressed, your shear stabilization is suppressed, your curvature stabilization kicks in and stabilizes the ideal ballooning mode. In negative triangularity case, though, that transition from negative shear to positive shear happens farther out in the bad curvature region. So we still have this area of zero shear, but now when this is happening, there is no good curvature to suppress the ballooning modes, and so we're just triggering the ballooning modes right away. This is that same thing, just in 1D. I don't know if it's easier to understand or not. Negative toroidal angle to positive toroidal angle. Good curvature here is in gray, bad curvature is in white. And you can see that this zero crossing happens very strongly in the bad curvature region for the negative triangulated discharges in red. And so this is kind of the whole game, is that it's all about shear stabilization on the edge. And because it's linked to your shape change, it's really, really robust, right? So just one other way to visualize this. This is a plot showing the distance to a stability boundary, max alpha ped minus min of alpha ballooning, the distance to your stability boundary. It's a function of the D3D database for lots and lots and lots of shots. All of our discharges with triangularity less than minus 0.3 live in this area down here below the first stability limit. Whereas all of the discharges with more positive triangularity, I mean, these are still negative, but they're more positive, right? Live way up here in second stability, and you're able to get H modes. So notably, this is just like a super stark contrast, right? You're kicking in an ideal ballooning mode, and that sets a limit that you can't pass. It's a really strong MHG limit, so it's not fragile like some of these other ELM-free modes. It's really, really strong. But notably, and can debate how long to talk about this, but notably, this is not the end of the story, right? This is the pressure at the pedestal location. There's a huge range in pressure at the pedestal location for the negative triangularity discharges. And there's not all the negative triangularity discharges are right at the stability limit, right? There's others that are down here, even at very high power. So there's more physics going on than just the ideal mode, but the ideal mode sets like an upper cap that you can't ever get by, right? So it's like basically the maximum limit is still lower than where we want to be. Does that generally make sense?
Is the ballooning mode a disastrous instability? Like if you try to get there, it ruins everything, or does it just limit, like quietly limit you?
Yeah, in the 70s and 80s, we thought it was disastrous because it was limiting you, period. But it turns out that it's okay. And so the real thing that we would want to not do is produce high peak heat fluxes on our divertor, right? We don't want to melt our wall. And so that's kind of shown here, right? If you look at the full range in heat flux, there's spread as we go this way. But the dangerous parts are the highest heat fluxes we get. When the ballooning stability is kicked in, our heat flux is constant, but it's relatively low. And then as we get rid of the ballooning stability and transition to the peeling ballooning stability, our peak heat fluxes get much, much higher. So this is similar to like a small ELM regime, kind of, where we have like lots of really tiny ELMs that are depositing small heat fluxes. Except it's even smaller. It's just like average it all out to be constant, right? That's in theory the lowest peak you can get if you just have the average, and then you just have to debate how high is that average. Is that low enough? And NT helps with that too, but for reasons we haven't talked about.
between the first and second stability region, there is actually a gap or what?
Yeah, so I mean, here you can see, sorry, here you can see a bit of a gap, right? So first stability region, if you get limited, you're going to be stuck here. If you're not limited, you're going to go all the way up to the peeling ballooning region. And so there's going to be a gap in the plasmas.
So why can't, I'm just trying to understand why cannot something be in the second stable?
Something stable here?
Yeah.
You can.
You can?
Yeah. All of this is just different ways. I mean, when I talk about this in seminars with the students, this is all just different ways to poke holes in the bucket. So I'm showing you one way. The ballooning mode is one way to poke holes in the bucket. But in EDA, QCE, other acronyms, you have a QCM. We love our three-letter acronyms. A quasi-coherent mode, which is a different mode that pops in under various conditions, which pokes holes in the bucket. In I modes, you might have an edge harmonic oscillation, which pokes holes in the bucket, right? Really, you need to do something to induce additional transport across the pedestal, and these are all those different strategies to do that. Yeah.
Main question.
Yeah.
Why do you need the chamber to be like meters long, and why is it not something very small or something? I'm thinking of like the buckets, so maybe a big bucket would help.
Yeah. Because of one main thing, which is that so tokamaks are using magnetic fields to keep the plasma from moving out, right? We'll move along magnetic surfaces less fast, like across the magnetic surfaces. Because we want to get to fusion relevant conditions, way back in these like original slides, right? There's three parameters that we have to get really high. We have to get NT and tau, and actually the product of all those three to be high enough. Lasers have a very, very short tau, but they have very, very high T and N. They're super, super dense, right? Tokamaks reduce your T, reduce your N, and in turn, you have some sort of larger tau. So you have to basically keep your plasma around for long enough. If your device is too small, no matter how strong your magnetic field is, you're just going to transport across your magnetic field before you're able to get enough fusion to sustain fusion. If you increase your magnetic field, you can hold it there longer, but you still need to have it big enough that it doesn't just drift away. So there's two main approaches to get to fusion relevant conditions. Those are spark and eater. Eater is like even bigger, giant. And spark is smaller, more magnetic fields, but it's still fairly large. These are going to be big machines.
Is that the reason why Pizza is the only one with that normalized beta in the range that you want, so that it's bigger, or?
The beta is a little bit independent of this. It depends more on like the actual properties of the plasma. It's really the energy confinement time that sets the size. Yeah.
So, what about the disruptions?
What about disruptions?
So
Yeah.
does NT improve the situation or make it worse, or do you know?
The short answer is we don't really know for sure, but
Does D3D have disruptions?
D3D does have disruptions, yeah.
They are certain. Like as an experimentalist, does someday you just have a disruption, or
Some days you just have a disruption.
is that right?
Yeah. Even on D3D,
With
it's
all your control.
with all of our control, yeah. I mean, so this is if we wanted to run D3D in a non-destructive way, we could, right? We could choose a boring plasma and run that over and over and over and over and over and over again. That's hopefully what we want to do for a reactor. We're not trying to push the limits, but people are always running experiments on D3D where they're trying to get to the peak this or the peak that or try this, and those push the plasma into places it doesn't want to be. That's one of the benefits of NT actually, is that in the disruption sense, and these are all a little bit hypothetical because we haven't done like a full, really robust study of this yet. But NT is a little bit more boring of a plasma. It doesn't have crazy gradients in the edge. It doesn't have crazy edge oscillations. And so it's a little bit more stable in general, and it responds better to actuators. So if you were trying to run a boring plasma, like the most boring plasma is an L mode, the second most boring plasma is an NT. And so it's a good strategy in that direction. When we were running the D3D campaign, we weren't particularly concerned about disruptions because disruptions on D3D aren't game ending. Disruptions become game ending when you have a ton of plasma current, like you would in a reactor. So on D3D during the NT campaign, we weren't really trying to avoid them, so we don't really have good stats of how easy they are to avoid. But
Yeah,
it should be about the same.
B fields are low. I mean, not D3D has.
It's low B fields, low stored energy, low IP.
Low force on them.
Low force, yeah. There are some bigger machines in the UK where you have really bad disruptions. But D3D can tolerate disruptions all day long and not be a problem.
But for the NT campaigns at D3D, has disruption ever happened?
There were a couple, yeah,
There were a couple.
absolutely, yeah.
So
I mean, as we were trying things, some in the beginning, we just had the wrong control scheme, and we were losing the plasma vertically all the time, and then we fixed that, and then that didn't happen anymore. There are still disruptions as people were putting in. I mean, okay, we can just bounce around, yeah.
So what's the downside of having a disruption? You have to wait a while to.
So on D3D, there's not much of a downside.
Not much.
No.
It just happens and you say, oops.
Oops, yeah. I mean, some experiments, we had an experiment last week that was purposely trying to determine disruptions every shot. So they're just disrupting every shot to look at what happens. D3D is small enough where that's okay. In something like Spark, you could probably tolerate dozens of disruptions. And then you would be ripping your magnets out of the ground and bending your steel, and the whole machine would kind of compress and explode. So the more stored energy there has, the more forces you're depositing in the wall, and eventually it's just so much force that you really can't deal with it. Yeah, so it's a future problem that's staring us down, but we'll get there. NT, yeah, the story for disruptions for NT is a little bit hopeful because we think they're simpler plasmas, but it's not necessarily guaranteed to be better. One of the examples of a cool physics thing that is related to this in NT is the density limit. So one of the ways you can trigger disruption or a loss of confinement in plasmas is having too much density. And we have this thing called the Greenwald fraction, which is basically an empirical scaling that says once you get your density above the Greenwald fraction, that's too much. We can't handle it, and the plasma either goes through like a radiative collapse or a disruption or something like that. So Greenwald of 1 is your limit. In negative triangularity plasmas, we were able to get to Greenwald of 2, which is crazy. Like that's never been done before. And it's really because with added beam power, you can actually modify where this empirical scaling ends up. Your transport's a little bit different, your stability is a little bit different, and so you can get to higher Greenwald densities. And so that's kind of shown here. These are all negative triangularity plasmas. These are full pulses as a function of time. And the line average density over the Greenwald density is plotted in this graph down here. Yeah, that's right. And so this was basically like a scan without any beam power. You would go up to the Greenwald of 1, and then the line abruptly ends. We had a disruption. We lost control. It abruptly ends. It's over. With added beam power, you can get higher. With a lot of added beam power, you can get all the way up and then not disrupt. You can come back down slowly and kind of finish the pulse out. And so this was a really, really cool result. That was a bit unexpected in negative triangularity, basically pushing these plasmas, which were all limited by the Greenwald fraction of 1, up to higher Greenwald fractions, which kind of suggests an alternative path for reactors as well. Every H-mode reactor that's ever been designed has had n Greenwald of 1 be their hard constraint for the maximum density they're allowed to play with. But for NT, that might not be a case anymore, right? So we might have more flexibility in spaces like that.
So is that because in NT more particles live in a lower B field region? So somehow you can pile that up more before you go to something.
Somehow, yeah. I mean, to be honest, this isn't quite well understood yet. The Greenwald fraction itself has been around for 20 years, and we still don't really know the theory behind where that comes from. It's an empirical scaling, very, very simple, I over plasma current over pi times minor radius squared. But theories, more complicated theories to describe it haven't really borne too much fruit. But yeah, in NT, you can, with higher beam power, probably because of the inferred particle transport, you have more particle transport. You're flushing out more density all the time, and so you can get to a higher stable number. Cool. Yeah, please.
Do you have, while you're performing the experiment, do you have that data? That's you, for instance, for the green one, you said it's disrupted and the blue one just continues. So do you have that information while having the experiment?
Yes, we do. So on D3D, there's a bunch of real-time signals. There isn't any time to do anything, right? But you can, like, you can't say, oh, our density is going too high, and then manually say no. But you can program a controller to like have a limit, and then the controller can look at what's happening in real time and modify something. So shape control is done this way, where we're actually measuring and modifying the plasma in real time. Density control is done separately. We can specify a density target and try to get that density target by puffing in more gas or not. And then that's usually of like a lesser fidelity data. The very high fidelity data comes a minute to 15 minutes after the pulse. And that's what we use for the physics analysis. But that's still on the same cycle time of running the experiments. We'll typically be taking a shot every 15 minutes. So you can see like the really good data from your previous shot before you make decisions for your next shot, something like that.
I asked this, and it's actually good to know that it's every 15 minutes, because if you have so much data, and if you could feed all that information, then you could just group it into a machine learning model with clustering, disruptions happen, disruptions don't happen. And then while running the experiment, it could also inform you the possibility of having a disruption, and you could just change your.
Yeah, absolutely. Absolutely. That's a really great idea. It's something one of my colleagues at Columbia is working on, and our colleagues at MIT as well. Disruptions happen really, really fast. They're just kind of snap events. So once it's happening, the only thing you can do is like hope or put in, I mean, there's strategies to like, put in a bunch of pellets, massive gas injection to try to reduce the damage, but it's like, you're not really stopping it. The real thing we want to do in a reactor is predict it a second ahead of time and avoid it, right? So you can see these cool, sometimes ML, sometimes theory-based models where like your plasma is heading into a disruptive space, but then you can turn it in an actuator beforehand, like steer it in a different direction. It's all based on likelihoods and stuff like that. Yeah, it's really cool stuff. Yeah, Steve.
Maybe a super extended question. Is there any meaning in panel C to the fact that all your shots basically approach the Greenwald limit, go flat for a bit, and then go up? Was that controlled? Did that happen without?
This was controlled. Okay. Yeah. This was a set of it. These are all from one particular set of experiments that we ran during the campaign. And it's like get to a stable condition, establish a stable condition, then a ramp from there.
And so if you just tried to ramp straight up from the beginning,
it might be a little different. The stability of tokamaks in general is time dependent. So you can't just go to a condition and have the same stability and performance that you would if you went to that condition a different way. And this is all because there's diffusion, there's current diffusion, there's like settling in of flux lines all simultaneously happening. And so if your current profile looks different because your flux gets frozen in a different way, then your transport's different and stuff like that. So it would look a little bit different. If you ramp too fast, you just blow up. But yeah. Running a little short on time. Wanted to show one cool thing, I think, which is just a comparison of these different regimes that we've been talking about. So this is a comparison of several different ELM-free strategies. This is from a paper from 2021. There are the strategies that aren't listed here. This is just a picture of a paper. Each one of these, so enhanced D alpha H mode, I mode, negative triangularity, quiescent H mode, and resonant magnetic perturbations is basically a strategy to avoid the ELM problem. To be viable for access to a reactor, it not only has to avoid ELMs, but it needs to do a bunch of other stuff simultaneously, right? And so those are kind of listed on this y-axis. You have to be able to get to high total power. You have to have low power compared to your LH power. You have to have low injected torque. You have to have low Q95, low collisionality, et cetera, et cetera. So these are just different sort of criteria that we have to get to. And importantly, you have to do them all at the same time. So that's not really shown here. But this is kind of the status in 2021 of all these different regimes and how they perform in terms of these things. After we did the negative triangularity experiments in 2023, the negative triangularity line just lit up entirely green. And I've also plotted here in stars criteria that will access simultaneously. So basically like two types of scenarios of negative triangularity that we were able to achieve on D3D in this first campaign. One of which hit all these buttons and one of which hit those buttons. So it's getting really close to being applicable, right? I kind of crossed off this one in the middle because we actually think maybe for negative triangularity, the low collisionality is not actually a constraint. Your reactor is going to optimize a bit differently. You're going to build your machine a bit differently and not need that anymore. So it's really promising in terms of being able to provide access. And then just to like I don't know, maybe give a hint towards where this would go in the future. We can do a bunch of optimizations to look at how this changes in a power plant compared to an H-mode reactor. Negative triangularity and positive triangularity are going to optimize differently. So we have this cool code called Fuse, which takes into account all of the different physics laws we know about tokamaks and does this random variation with a bunch of optimizers, multiple objectives to try to identify different potential operating points. And so you end up with a big scatter plot like this, where you have a lot of different reactor designs. Some of them cost more than others. Some of them have higher Q95, which is basically like a proxy for disruption safety. You want to be somewhere on this line. And so you have a different sort of reactor space that's accessible for positive triangularity and for negative triangularity. These are both able to find solutions that look like they'd work for an FBP. Negative triangularity has a lot more radiation than positive triangularity in general. But more importantly, I think positive triangularity requires you to have P sol greater than PLH, two other terms I haven't really mentioned. This basically means that in order to get into H mode, to have that H mode performance boost, you have to have enough power crossing the separatrix to generate your pedestal. And this is what we've observed and learned, right? But that power crossing your separatrix then is deposited on your diverter. So if you're looking at compatibility between power crossing your separatrix and going to the diverter, that's really tricky to do. And if you look at, I mean, this is a plot of all the different solutions we've been able to find in positive and negative triangularity. P sol over R is kind of a metric for your diverter power. It's a really easy way to say, is your wall going to survive or not? If it's above 15, with our present technology, we think our wall's going to melt. Or at least this is what ITER says, right? So you can maybe choose a different number, but it's the same story. In positive triangularity, these are all pushing up against this limit. And if that limit is wrong, right? So if we have like, if our scalings, if our empirical fundamental physics-based empirical scalings for what this LH fraction is and how much power you actually need are wrong by a factor of 50%, all of the positive triangularity designs disappear. And you just can't find one that's compatible with your diverter. In contrast, the negative triangularity has a lot of solutions down here that have very, very, very little P sol over R. It's just more compatible with your diverter constraint because you don't need to dump all your power across the separatrix. You're never trying to trigger the H-mode pedestal, right? And so you can operate with a much lower scrape-off layer power. That's good.
Watts per meter squared is the critical parameter for melting.
Yeah, there's a missing 2 here.
No. PSOL divided by R is not the right units. I just wonder if there's a swindle here, but not. If the melting is determined by watts per meter squared, not
the over R comes in because at the larger R you are, the more you can play with your strike line to spread it. So that's actually a fairly subtle point. But
there's another direction.
Right.
So directions that have to be accounted for.
So that's one of the cool things about negative triangularity. So that this is what I'm sort of talking about by that spreading. You can take your heat flux and if you just hit an incident angle, you can spread it over a larger area, right? Positive triangularity, if we're looking at this, it puts the strike lines right in the middle of the machine at your lowest R that your machine's accessing. Whereas the negative triangularity puts your strike lines on the outboard machine. So there's just a lot more room out here to do something fancy with the diverter. The P sol of R kind of takes that into account, but there's actually like more benefit that's hidden from NT because you have this space. And so you could do something fancy. MassView is exploring fancy things. I think I maybe showed a slide about that last time. Yeah. So in summary, yeah, so I kind of think of negative triangularity as like an exhaust handling first path to a fusion power point. We are no longer trying to get the most power possible. We're just trying to get enough power to make it economically viable. And negative triangularity has a lot of advantages that let you get to an exhaust handling first perspective. It's kind of an apple over here where most of the tokamak research has been going in this direction. Maybe there's lower hanging fruit. We have lower power going to the scrape-off layer, larger R for a diverter. We don't have ELMs. The core confinement is actually a little bit better. We're able to get higher densities. I didn't talk about this, but it has much better compatibility with impurity seeding, which is another way to reduce your power because it flushes out all the density. There are still some disadvantages. There's a lot less data in negative triangularity than there is in positive triangularity. I think I mentioned in the beginning, like 99.9% of the data in tokamaks is positive triangularity. And so it's a little bit more uncertain to extrapolate it, although we think we have some ways around this. There's more challenging control. I have some slides on some new work that has a solution to that. There's predicted poor stability. This is why we didn't explore it in the first place. That's still true, but it's really not that much of an issue based on the D3D data, right? We're still able to hit those targets that we want for an FPP. And so really the questions are like, yeah, are there engineering risks we're not talking about or not noticing at the moment? How do these configurations optimize differently? How do we steer and investigate this in the future? But yeah, thanks for listening. Happy to stay around and talk about it.